Now we are coming to one part of the entire the process of building Linux to run on a embedded platform, which I am just going to sort of mention a few of the details over here, not really going to the too many details. The reason is that in practice we actually have some demonstrations where we have looked at how the kernel is compiled, how you can get modules compiled, how you can integrate everything and so on. What actually happens in reality is that rather than trying to do it manually at the kernel level, there are some kinds of scripts and programs that help to streamline some of those processes, right? So I'll just mention a few of them, but we'll not really go look very deep into those because they are very specific to the individual platforms, and especially if you are going into building systems for embedded FPGAs, then it is worth learning them in detail. But that's it, they are basically detailed, they are not really fundamentally different except for the fact that they make certain things easier and certain things a bit more complex to do. The first thing which we have already seen, of course, is the notion of cross compilation, right? The idea of cross compilation is that we have a host which is typically probably an x86 based laptop or desktop, but we are trying to compile for a guest or a target, and that target is probably an ARM system, right? So it's a different ISA, it's a different architecture, it's probably a different binary interface. So we need a cross compiler, and this term over here is usually what's called the cross compiler prefix, right? So you would have noticed that we used an environment variable, right, the cross compile, in order to specify exactly what kind of cross compilation we are trying to do, right? And by specifying this, we are saying that we are targeting an ARM processor running Linux, but more than running Linux, what is important is that this part of it, right, the GNU EABIHF, specifies something called the ABI, the application binary interface, which tells us various things like, for example, how does the Linux running on ARM expect functions to be called, how does it expect code to be managed, how does it expect the ELF files to look, okay. So there are sometimes occasional differences between how the same kind of files are managed on x86 versus ARM and other kinds of platforms, and all of that is captured in this part, right, the ABI, the application binary interface. GCC of course refers to the GNU compiler collection, right, the actual compiler that's being used for the compilation process. So this entire thing is usually given as a, or rather this ARM Linux GNU EABIHF is given as a prefix, and then there are various tools, GCC for C compilation, G++ for C++ compilation, LD for the linker and loader, AS for the assembler, and so on, right. So there are many tools that basically come as a package. All of them together basically give us the cross compilation tool chain. So the tool chain consists of the compiler, the binary utils, right, or bin utils, which is the assembler, AS, the linker, LD, and so on. A target library, right, a library is basically the C standard library, libc, the one that is required with our basic IO functionality and so on. One of the options that we have is what's called glibc, another one is called the MUSL, right. MUSL is typically for more embedded systems. It is a very compact, small set of functions and libraries, right, which makes it suitable for small embedded platforms. And in addition to this, there is also something called the sysroot, which is actually basically a file system, right, which contains multiple things that would be required when the OS is coming up, okay. So when you are cross compiling, you want of course these ARM binaries from building on x86 usually, right, or it could also be that you are actually compiling on, let's say, Mac OS, which is actually running on an ARM processor but with a different operating system, right. That's still cross compilation because it's not compiling for something that's going to run on the Mac OS. So the cross compilation itself is applied to compile a new kernel, and before we compile the kernel, we need to specify a large number of configuration options, right. We briefly looked at this when we were looking at the process of actually compiling a basic kernel, and as we saw there are literally thousands of configuration options, right, which control various different kinds of features that are enabled in the kernel. a lot of them basically decide on whether you want the ability to support different kinds of devices, in other words compile drivers for various kinds of peripherals, right. And in a lot of cases you might find that no, you actually don't want to have many of those, which means that if you remove them you could probably get a more compact kernel, right, or at least a faster compiling kernel. The problem is when you are creating something that's going to be distributed, you don't necessarily want to remove all of those options, right, which is where this idea of modules actually is extremely powerful, right. What it allows us to do is we can have certain drivers for certain devices that are built into the system, that are compiled in, right, versus modules which are actually present in the init RAM file system and can be loaded after the basic kernel has already come up by sort of probing for certain devices. And if the device is present, I load the module into memory and keep it there ready to be used. If it's not, then it doesn't occupy any space. So this deciding on whether a driver should be a module or should be compiled into the kernel, the main reason for it looks as though modules are always a better option. The problem is that there can be a scenario where I actually want the driver to be there right at the beginning. I don't want to wait until a file system can be read and then I can pull in a module from there. I want it to be able to detect and modify a certain device as soon as possible, in which case the only way to do it is actually compile it right into the kernel itself. Okay. So there are reasons for not using modules, although whenever possible it's probably good practice to try and use modules. There's very little of a performance penalty from the use of modules. That's not really the reason for not using them. You might find, especially if you are building an embedded system, that you actually want to disable a large number of unused features so that you can reduce the size. It might even mean just not compiling the modules, because even those occupy space on the init RAM file system, right. But of course at the same time you would like to have something which supports the kind of hardware that you are going to deal with, right. If you are sure that your hardware is completely under your control and you will never have to deal with another peripheral which is not already in your list, then you could basically disable a large number of options and have only the platform specific drivers over there, right. Now in the context of FPGAs and Linux, there are a few options that are typically mandatory. One of them is just the basic device tree support, right. But apart from that, the whole approach of using platform devices, because that gives us the ability to use the platform drivers, which as we have seen are a very flexible way of implementing device drivers, right. The contiguous memory allocator, the generic interrupt controller, these are pretty much mandatory things when we are talking, especially because we are trying to have custom peripherals which are going to use interrupts in order to communicate with the processor, and B will probably require some kind of DMA in order to get data back and forth, right. And one of the other things is this framework called FPGA Manager, which is something provided by Xilinx as something which can be used for managing the bit files on FPGAs. Okay, so all of these are sort of common configuration options that are highly specific to when you are building something on the Zinc series of processors. So just a word about the different kinds of build systems that are available. You might have noticed that actually I did not use either of these, right, in the demos. What I actually did was directly go in, get a stock kernel by downloading it from kernel.org, making some basic configuration options and compiling it, which is perfectly fine, except that there are programs and systems that help you to automate the process of building a complete bootable system. One of the things you probably noticed is the initramfs that we created was very tiny and very basic and compiled directly into the kernel, right. It's not straightforward to create a so-called SD card image and so on using that. Instead, there are other approaches. One of them is called build root, which is basically very similar to what we are talking about. It's make based and it's good for prototyping, and it can generate SD card images that can be used in order to directly boot a system from an SD card. Since we were only working with Renode so far, we have not had to worry about SD cards, but when you want to build something that's working on hardware, you will need to do that. Now, industry on the other hand prefers more complex systems, but which are capable of better customization, One of the most popular is what's called Yocto, right? It allows you to basically add on multiple layers and is a very flexible way of creating fairly complex boot systems, right? It's more or less an industry standard at this point, at least within the context of the Xilinx Zinc FPGAs, but that does not mean, as you can see, it's not the only approach that can be used. It happens to be probably the most popular one currently in place. It does have a much steeper learning curve than Billroot, which means that you have to spend more time to actually get to grips with it. Alright, so to sort of summarize everything that we have talked about so far, right, we started off with a discussion about boot sequences, right, the process by which we go through ROM, multiple different bootloaders, U-boot, eventually the kernel and user space, right. We also discussed about where we might want to introduce the FPGA bit stream into the system, either very early in boot.bin or in U-boot, or perhaps at runtime. We had quite a bit of a discussion about memory, right, in particular why virtual memory, how it's implemented, and what role the MMU plays over there. The fact that certain kinds of things like reserved memory are required for operations like DMA, and how the IO MMU can basically add security for DMA transactions which otherwise could potentially lead to direct physical memory access. And finally closed out with a very quick sort of overview of what exactly is are the concepts of cross compilation and why do we need build systems and how they can help to automate the development of embedded Linux systems. Okay. This did not really go into the details of how the different build systems work. It's more sort of meant to just tell you that different systems exist, and as the choice of what exactly you use depends on the context within which you are trying to build an embedded platform.